Good morning, everybody. Can you hear me well? Okay. So we will continue. I will finish the first lecture this morning. So we have a few formal things to finish. I mean, especially I want to look at large deviation for problems with dynamics, and then we will go to the second lecture with the first application to turbulent flow. So I want to stress before I begin that I will show you application for turbulence, but actually large deviation is used all over the science, in ecology, in finance, in economy, in biophysics. So it's something which is very developing fast, and it's of course it gives you only answer for specific kinds of question, but sometimes it proves very useful. So yesterday we stopped at the proof of Cramer's theorem. So maybe you remember Cramer's theorem is this theorem that gives you the large deviation rate function for the sum of identically distributed random variable. And then you have just a formula. You can just plug in the formula and compute directly the large deviation rate function for any distribution P naught. So a natural extension of this is to look at large deviation for the empirical distribution. So here, rather than looking at just the sum of n independent variable, I will look at the histogram that are produced by this n value. And so here, this delta is a Dirac delta. So it's delta of x minus xn. So you just look at where you got the point on the histogram, and then you make the average. So rho n is the histogram, and when n is going to infinity, you expect rho n to converge towards P0, where P0 is the distribution of the independent value of xn. But if n is small but finite, large but finite, then you expect some large deviation rate function. And so then the logarithm of Pn is equivalent to minus n multiplied by some rate function. And this rate function, when you look at it, it's rho log of rho. So that's why you have rho log of rho everywhere in physics and in many other applications, in information theory and so on. And so here it's rho log of rho divided by P naught, where P naught is the reference measure. And in this case, the reference measure is the measure of the probability density distribution for the xn. And so this is a very powerful and very important result. This is called Sanoff theorem. And so it generalizes Cramer's theorems when you, rather than looking at just the sum, you want to understand the behavior of all the distribution. Okay, so now I want to go towards dynamical problems. And so I will discuss dynamical large deviation. So it's also called large deviation for path measures. Path here means that it depends on time. So it's a process. It's a stochastic process, something that depends on time. And we look at the large deviation for this process. So that's why it is called dynamical large deviation. And so I will begin by the most simple example for this, which is the large deviation for stochastic differential equation with weak noise. And then we will generalize this to other problems. So in order to illustrate the problem and also to make the connection with bistability, I will take the simplest possible problem in dynamics for which you have bistability, which is called the Cramer's problem. So Cramer's was working in the 1920, 1930, 1940. So around 1930, he wrote this simple stochastic differential equation. So you have dx over dt is minus dv over dx. So you see the x is the position of a particle, for instance. Minus dv over dx, it means that the particle fall following the gradient of the potential v. And so here, for instance, I have plotted an example of a potential. So you have x and v. And so here you see that the potential has two local minima and a potential barrier. And so this is an example with where you have two attractors for you have -1 and 1. So you have two attractors when you have only this part of the dynamics. But then you can add some noise, some Gaussian noise. And so, for instance, this noise can be understood in equilibrium statistical mechanics as the interaction between the particle and the thermal bath. And then you have a noise which is with a coefficient here, which is square root of 2 kBt, where T here is the temperature. And so then if we have this dynamics, because of the small noise, you have small fluctuation around -1 or small fluctuation around +1. But very rarely, the noise can push you above the potential barrier and you go the other side. And so this is what you see here on this dynamics. So this is just a numerical simulation. You have T and X. So you see T has been divided by 1,000. So it means that here we are looking at time scale, which are thousands of typical time scale for the fluctuation around the minimum here. And so you see that the dynamics fluctuates around 1, suddenly it jumps around -1. And so you have random jump back and forth from one attractor to another. And so it's exactly the situation. It's the simplest model for the situation you have in chemistry, in physics, in many other contexts. And so the point of Kramer's, his goal was to actually derive the Arrhenius law for this case. So the Arrhenius law is the fact that the rate to go from one attractor to another, it will be proportional to exponential of minus delta V divided by kBt. Okay? And so this is just like the Arrhenius law, where here the potential barrier value is delta V. And so this is the energy that is exchanged with the thermal bath. And so if you plot the PDF of the transition time, the time you need to wait to have a transition from the attractor 1 to the attractor -1, and here it's a linear log plot, and so you see that there is a straight line, meaning that the waiting time is nicely exponential in this case too. So it is exponential. Mathematically, it is exponential in the limit when the noise is small, and it's the limit when kBt is much smaller than delta V. Okay? So what Kramer's did is to write the Fokker-Planck equation for this problem. And then this Fokker-Planck equation, he made some asymptotics analysis, just like we do often in fluid mechanics or in many other fields. So much asymptotic expansion and so on and so forth. And he derived the rate. And so these kinds of expansion have been generalized in the 60s and 70s, for instance, by Langers and others, in cases for which the dynamics is not in dimension 1, but is in dimension n, where n can be anything finite. And so what I want to show you today is that a more modern approach is to use a path integral formulation or large deviation theory. This is actually exactly the same for me. I mean, physicists use path integral formulation. And when you put this correctly in a mathematical framework, it gives you a large deviation theory. And so the point of this large deviation theory approach is that it will be valid for a much wider range of dynamics. Okay, so for this, I will need to discuss the distribution of a white noise and explain you better what is a Gaussian white noise. So I do this very formally, roughly. I just give you a very simple qualitative explanation. So for instance, you consider a Gaussian vector eta. So here you have just a finite number of entries, eta I, with I between 0 and capital I. So the average is 0, and their covariance is just delta ij, right? It means that they are uncorrelated one with the other, and they all have the same variance. And then if you write the PDF of this, it's just exponential of -1/2 sum of I equal 1 to capital I of eta I square. So there is a coefficient here 1/2 for all of them because they all have the same variance, and there are no cross correlation. So it's very easy. And so this is just a normalization factor. And so a Gaussian stochastic process with correlation function delta of t minus t prime, what we call the Gaussian white noise, is something for which you take a limit of this by putting this by interpreting I as a time step, and then you take the limit where the time step goes to 0 in order to have a continuous path. And when you take this limit, formally, you can write that the probability of the white noise is proportional to the exponential of -1/2 the integral of 0 to t of eta square of t dt. And so you see it's a square because it's Gaussian. There is a single integral because there is no cross correlation. And then, and so here I have not written the prefactor because actually if you think about it, the prefactor will diverge. And actually mathematicians don't like this to work this way just because it's formally you understand well what you do when you discretize, but as soon as you try to take limit, it's a bit tricky. But still for us, it will be good enough. So I will work with this. And I would just say that I don't care anyway with the prefactor because when I compute large deviation, I don't care much about that. We can do better as physicists to compute actually the correct prefactor, to actually correctly normalize things. I mean, those are typical subjects in statistical field theory, but I don't need to go in this detail today. Okay, so now you know what is the PDF for eta here, because by definition, eta is such a Gaussian white noise. So then if I want the distribution for x, the path x, so you see I will consider x of t, my path for the dynamics, with t between 0 and capital T. And then if I want to know the distribution for x, well, I know the one for eta, so this is an equation. So I just have to make a change of variable. So it's a strange change of variable because it's with respect to time, you have time derivative and so on, but still it's nothing else than a change of variable. So I start from the white noise probability written here, and then I make the change of variable. And formally, I get that the probability to see the path x will be exponential of 1 divided by 4 kBt. So you see it was the 1/2 here became 4 kBt because there is this 2 kBt here factor. And then here it will be eta is just x dot plus dv over dx up to this factor. And so that's why you have here x dot plus dv over dx to the square. And that's why you have a single time integral because it was white in time. And then here you have a Jacobian for this change of variable. But this Jacobian, actually, as I told before, we don't care about it, but actually it depends on the convention we use for discretization. And if we use the Ito convention, it is just 1. And then it gives us the probability to see the path x with this very simple formula. So if I do that, then if I want to compute a transition probability, for instance, I want to compute the probability to go from state x naught at time 0, x0 at time 0, to the state xt at time t. Then it's just like in quantum mechanics. So you can, I mean, the point is that you have time 0 and time t. So you start from x naught. You know that you are at xt. You can take any path you like. Any path is allowed, but for each of these paths, you know its probability. So you know it's the action of the path. The action is just, as we wrote before, it is A of t here, where A of t is the formula I got on the previous slide, right? Here you see, this is just the action you have here and the Lagrangian. Okay, so I can write that the transition probability is the sum over all the possible paths with this weight that comes just from a change of variable from the weight of the Gaussian white noise. Okay, so if you do it this way, if you write transition probability this way, so you will do exactly what Onsager and McLuhan did in 1953, I guess. This was just 3 years after Feynman wrote path integral for quantum mechanics. So it's then you have exactly the same formalism as the path integral for quantum mechanics. So usually it's very difficult to deal explicitly with this path integral. So one way to do something with them is to consider some asymptotic limits. And this is actually what we will do here. So here we are interested in the case when kBt is very small. It is much smaller than delta v. And then you see that in this integral, we have the exponential of something divided by a small parameter. So it's a Laplace integral, just as I explained you yesterday, but it's a Laplace integral for path. Okay, but it's the same rule, the same way to work with it. And so in quantum mechanics, it is called a WKB approach. More generally, it is a saddle point approximation. And then you can just look at what's happening in these asymptotic limits. So as I explained you yesterday, the leading order is given just by the exponential of the minimum of the function over the sets you are interested in. And so here, you have to look at the most probable path from x0 to xt. This is the minimizer of the action. So you just look at the minimum of the action with the constraint that x0 is x0 and x of t is xt. And so with these two constraints, then you get the action to go from x0 to xt. And that's it. You can conclude that you have a large deviation rate function where when the kBt goes to 0, the log of the transition probability is equivalent to this action, this minimum, divided by 2 kBt. Okay, so it's very, very simple and very straightforward. Okay, so if we do that for this case, we should be able to, if we take x0 equal to +1 and xt to be -1, and to take time t which is large enough such that we consider the fact that the transition between two attractors occurs on time scale which are much longer than the typical times of the dynamics, then we should be able exactly to find the result of Kramer and the Arrhenius law. And this is actually what we get. So when you do that, it's a simple exercise which is done in the lecture note. And so you find directly, it's very easy to do that. It's the exponential of minus delta v divided by kBt, just by finding the actual minimizer for this path. So I show you here the path. So here it's v is a bit more complex. Now I am in dimension 2. So I have two variables, x and y, x, y. I have a potential in dimension 2. So the colors you see and the lines are the level lines of the potential. And so you see that you have a minimum here and the minimum there. So you have two attractors, one here and one there. And here somewhere you have a saddle point in between these two attractors. And so this red line is the minimum action path. It's exactly what is written here when I take for x0 the first attractor and for xt the second attractor. And so this minimum action path to go from one attractor to another, this is what I will call an instanton. And so you see now this white path here, it is actually a sample, just one realization of a transition from one attractor to another for the real stochastic dynamics. And you see that it actually very nicely follows the instanton. Okay? And so you can think about that here from the point of view of this path integral. I mean, you know that the weight for computing this transition probability should concentrate close to the minimum of the action. So it tells you that most of the path should concentrate close to the minimum of the action. And you even know the level of magnitude of the fluctuation. The level of magnitude of the fluctuation should be of order of square root of kBt. And you can even expand this path integral at next order at any order you like and compute the correction. And so in this case, you can actually compute the prefactor and the correction. Yes?
Normally, I would have thought it would be kinetic energy minus potential energy.
Right.
But here it's dVdx, it's the force squared.
Yeah.
So I guess I'm kind of confused why it's not the normal kinetic energy minus potential energy.
Yeah, in quantum mechanics, it's you are right. It's kinetic energy plus potential energy for the most simplest case. But here, so here it's not. We are not writing the action for a quantum process. We are writing the action for this stochastic process. And so if we see where it comes from, everything comes from the noise statistics. Okay, so if I would have used another type of noise, it would have been different. Okay, so here it's related. You should really figure out what is the noise statistics. And for other problem later on today, I will show you how we can actually compute such Hamiltonian and Lagrangian directly for microscopic dynamics for some cases. So I have another question.
You know capacity of the time to go from 0 to
You can choose it. It's your choice. And then if you choose it, you are computing the transition probability from time 0 to time t, right? And for when you compute the rate, there is a bunch of slides I don't show you today. I mean, if you take capital T very large, then you are computing the rate which is independent from the boundary effects and which corresponds to this rate you are interested in for when there is a very good time scale separation between the average, the rate you compute and the time typical for the fluctuation of the dynamics. Okay, so all this is explained in the notes. They are a bit more detailed.
I just want to sort of comment. When there are models where you actually have Hamiltonian dynamics, it's more like classical.
Right, yeah.
It's as simple as possible.
But as you will see later, we will see many other examples, and you will see that depending on the physical processes involved for this fluctuation, the Hamiltonian are quite different. Okay. Yeah. Yeah. Yeah, right. Yeah, so as I told you, this is just the simplest case. Later on, we will see other kinds of noise, even some noise that are produced by just the Hamiltonian dynamics of interacting particles. So I don't know. I mean, some kinds of noise can be dealt with. Some others, it's more difficult. So if you have a color noise, for instance, as you asked, it depends. I mean, it depends whether the time scale for correlation, how it compares to the other time scale in the problem. Sometimes there are large deviation results. Other times it's not the case. So it's okay. Sebastian, you had a question too? Oh, sorry. Yeah.
Looks a little bit like the quadratic function, which
absolutely. Yeah. Here, when you do this large deviation theory for equilibrium statistical mechanics, you exactly find what you say. You exactly find that the thermodynamical potential are large deviation rates, and that the cumulant generating function are just the conjugated ones. And so that's why you have the Legendre functional transform between them. So here it's in a sense, it is just like thermodynamics for other problems. So the equilibrium statistical mechanics case is, there are many simple examples that are treated in the lecture notes. Yes? For this simple problem, you are right. The most probable path does not depend on the amplitude of the noise. It is really a property of the limit. So here, the red path does not depend on the amplitude of the noise, but the level of the fluctuation around it depends on the amplitude of the noise. So some work we have done with colleagues, some theoretical works, is to work out the prefactor here. The prefactor were computed for these equilibrium cases when you have a dynamics with a V, but we have worked out formula which are valid even out of equilibrium, but I don't go into this. So let me go now to more general things where we don't assume that the noise is Gaussian and white. So another way to think of this Lagrangian is to say that we look at the probability that x epsilon of delta t minus x divided by delta t. So you see, this is just a Newton ratio, what you compute when you want to compute a time derivative. So, but here, rather than computing just the limit, we want to compute the limit of a distribution. So that's why I write delta of this Newton ratio minus something that I want to have as an objective. So I denote it x dot because it's just a time derivative. And so if I can compute that this distribution here, so it's a function of x dot, condition on the initial condition, which is x. So if I can compute that the average of this is logarithmic equivalent to exponential of minus delta t multiplied by L of x dot divided by epsilon. If I have a Markovian approximation such that I can reproduce this and add them together, then I will get that the probability for a path goes like the exponential of minus 1 over epsilon multiplied by the integral of 0 to t dt of L of x and x dot. So you see, if it is Gaussian as before, then you just get the quadratic Lagrangian I discussed before. But here you see I can generalize that to anything. And so if you use this, then in order to compute this quantity here, the limit when delta t goes to 0, you should use what is called the infinitesimal generator of the stochastic process, which is a tool to compute average of some observable applied to the variable x minus their value at 0 divided by delta t. So this is again a generalization of the Newton ratio for stochastic process. So I am a bit fast here, but you can read this on the note. So if I use these tools, it's not difficult. It's just something that you can learn in 1 or 2 hours. Then there is a general result that is simply to derive as theoretical physicists do, which is that if you can compute the limit when epsilon goes to 0 of this infinitesimal generator applied to exponential of px divided by epsilon, multiplied by exponential of minus px divided by epsilon, and multiplied by epsilon. So you just have to compute these limits. Then immediately you get the large deviation principle, where the probability that x epsilon is equal to x is the exponential of minus this action divided by epsilon. And here you have the classical relation between the Lagrangian and the Hamiltonian. And so you have a formula to compute the Hamiltonian, and then you use the Legendre functional transform to compute the Lagrangian, and you get your action. And so there is a very general way and very simple way to do this. Let me apply this to a few simple examples. Yes? So here you see, so in general, there is in general, this Hamiltonian has nothing to do with the Hamiltonian of Hamiltonian dynamics. So here it is an Hamiltonian for the large deviation probability for this path. So later on, I will deal with kinetic theory, and then we will be able to make some connection, maybe. And so the question you ask is there a symmetry related to time reversal symmetry? And so I will come back to this later. It's time translation. Oh, okay. So yes, if your process is homogeneous in time, if the transition probability depends only on the difference between times, then the Hamiltonian do not depend on time, and then you have a time translation of the action, and then because of the time translation of your action, if you apply Noether theorem, you get a conservation of the value of the Hamiltonian along the minimum path. And so, for instance, if you compute the value of the Hamiltonian along the instanton, it will be conserved. That's right. Yeah.
It's probably convex.
Yeah. By definition, this Hamiltonian, because it's a large deviation right function, there is a general property that tells you that it is a convex function with respect to P. And actually, whenever locally it is Gaussian, just like the Gaussian noise, it is quadratic in P. But it is always convex. So let me give you a very simple example, just to show you that we can go beyond white noise. So here I consider just radioactive decay. So you have particles, and then they have a rate to decay, right? So you have a state 1, and you go to the state 0. So this would be the radioactive element, and this would be the element without radioactivity. And so then you have a rate to do that. So the event will happen anytime with a rate lambda, okay? So it means that if the event has not appeared yet, the probability to get the event in the next time interval dt is lambda multiplied by dt. Okay, so it's just the radioactive decay you have learned maybe in high school already, or okay. So it's what is called the pure depth process. But rather than looking at one single particle, I will look at n of them. So I have a sample of something. There are n particles inside the sample. And then I will measure the average of the decay over time. And so I have n independent particles, they each decay independently. And then I just compute the average. Xn of t is just 1 over n, the sum n equal 1 to n of xn of t. And so you see that xn is initially all xn are 1, and then they decay to 0. And so this xn of t should decay. It has to decay. It starts at 1, and then for a very long time it would be 0. But the question is, how does it decay? So of course, if n is very large, you take the law of large number, then you just write that, making averages here, you just write that dx bar over dt is minus lambda x bar, and you find that x bar is exponential of minus lambda t. So this is what you expect. The average decay is just follow the exponential. But the question is, what are the fluctuations around this exponential? Can we deal with this? And then you look at the probability that xn is equal to x. And so you can, using the rule I said before, write a large deviation rate function where you get the exponential of minus n multiplied by some action. Then it's a very simple exercise to compute the infinitesimal generator. It is written here to compute the formula for the Hamiltonian I wrote before, and I get an Hamiltonian, which action is here. So you see it's proportional to lambda, which is the rate. It's proportional to x because it's proportional to the numbers of particles that are not decayed yet. And then there is this exponential factor, exponential of minus p minus 1. So this exponential minus p minus 1 is what you get when you have a Poisson process. And this is actually when you have an exponential decay. Every time you will see this exponential factor, it's related to exponential decay. So then I very easily computed this h. So from this h, I can compute the L just by making the Legendre-Funchal transform, and this is the L. And so the point is that when I do all the math, it gives me automatically that x dot should be negative, as it should. And otherwise, it gives you exactly the value of the Lagrangian. So when you write you see this Lagrangian, you see that H is not quadratic in P, so it's not Gaussian at all. So it's the noise associated to these jump processes. And the Lagrangian is not at all quadratic in x dot. It has this very funny shape. But you can do this. It's very easy to do. And so, for instance, if you are studying ecology problem, so typically population meet randomly, and when they meet, they can react just like chemical species. And then much often, when you are studying large deviation for ecological process or for chemical reaction, you have this Poisson type statistics, and you get these exponential factors. And then if I ask what is the most probable path here, then I get the relaxation path I already knew from the beginning. Okay, so I can generalize this to many other things. So I give you just another simple example because it will be useful for the, yeah. The small p here. Okay, so you see the it is the, so yeah, this is a very good question. So here we have seen that L of x dot, it is related to the PDF of the probability to see x dot, right? And this gives you L of x dot, right? If rather than looking at this PDF, I look at this cumulant generating function, I will have a parameter which will be conjugated to x dot. And so P is a parameter which is conjugated to x dot. And you see here in the Legendre-Funchal transform. Okay, so that's why you get always the same formalism as the one in classical Hamiltonian theory. You have, so P is a parameter that you multiply by x dot. And so then you look at all the possible value of P and you take the supremum. Okay, so here just for this problem, P is just a variable that has the same dimension as x dot and as you use to make the computation. Okay, let me now give another simple example where you have a network of reacting particles. So I have n particles xn. So each of them can be in k different state. So xn can be equal to k with k between 1 and capital K. So the numbers of particles which are in the state small k is called n multiplied by fk. It is intensive with n. And so then I will look at the empirical distribution, I mean the value of this fk, right? Now I will assume a dynamics, and the dynamics here is just that the particles have reaction. So you can, the particle of type K1 can meet the particle of type K2, and then they will react giving particle of type K3 and K4. And I call the rate lambda divided by n. Okay? And so you have a two-body reaction with rate lambda which are given. Now I take the limit when the numbers of reaction per unit of time is of order n, and the numbers of reaction per particle per unit of time is of order 1. And I look at how this distribution evolves, and then I look at the probability that Fn is equal to F, and I get a large deviation rate function using the same rule as before. So again, I don't do the computation today, but it's easy to write the infinitesimal generator to compute the formula, to use this general formula for the Hamiltonian and to compute it. And if I do that here, I find that I have F, I have a P which is conjugated to F dot, and then the H is just the sum of all the possible combination of K1, K2, K3, K4. There is this rate lambda. Then there is a product of 2F, the incoming particle. So you have the probability to see the particle 1, the probability to see the particle 2. Here the particle by definition will have processes which are uncorrelated. And then you have this exponential factor here, exponential of P minus P1 minus P2 because you have lost the particle 1 and 2, and plus P3 plus P4 because you gain the particle 3 and 4. And you always have this minus 1. And so you see this exponential here come from this kind of reaction between particles. Before, in the case of radioactive decay, you had just one particle and it was decaying. So that's why it was exponential of minus P minus 1. Okay? So it's a very simple example that will be useful later on. Let me finish this by defining what is called the quasi potential. So let me assume that I was able to prove such a large deviation principle for some path. Now H or L can be anything. Well, H has to be convex with respect to the second variable, but they could be anything. So one thing that is important is to relate this path large deviation to the static distribution. So to the, for instance, to the stationary measure of a process. And so here I assume that the process is stationary and it has an invariant measure. And so I now look at the invariant measure, whether it has some large deviation properties. So I look at the probability that x epsilon is equal to x, but now I have no notion of time. It's just at any time, I just look at the probability that x epsilon is equal to x. It's the invariant PDF of my system. And I define, if there is a large deviation principle, then the large deviation rate function for x is called u of x. And it is called in the large deviation theory a quasi potential. It is called a quasi potential because when I have a dynamics with a potential, like the case I was considering before, then u and v are just the same. But here it generalizes the notion of a potential to any dynamics which is statistically stationary. Then if we assume that u as a single minimizer, there is a single attractor x naught, then the probability to see a very rare value of the PDF, well, you can just compute it from the action. So you say that you started at minus infinity close to the attractor. So you impose that at minus infinity you are at x naught, the attractor. You impose that at x of 0 you are at x, and then you compute the minimum of the action. So it means that to see a very rare, so here you have your attractor, to see a very rare fluctuation that arrive here, it will give you the probability to be here by. So you just have to minimize the action to go there through this action minimization. And so this, the path that minimizes this action here is called a fluctuation path because it is the most probable fluctuation that leads you to a state x here, which is anywhere in the phase space. And so it means that if you know L and H, if you know the dynamics, you can compute the quasi-potential this way. So it means that what happens in practice is that, so you have your attractor x naught, You start from anywhere in your phase space. You will soon converge to x0, okay? It takes a time which is relatively small, and then you will stay there a very long time. So you will have a typical fluctuation of your system. And then you want the probability to be here. So it's a very rare event to go there, okay, because you are not in the part of the space where you have typical fluctuation. And then you will wait there, you will wait there a very long time, which is exponential of minus something divided by epsilon. I mean, this something is actually related to you. And then finally, you will manage to do it. Okay? So that's why you can, so here this is a finite time to relaxation. This is a finite time to fluctuation. But I mean, you can consider that you start from x0 at minus infinity, because anyway, you will wait here an extremely long time. You can, well, there are different, so you have time scale. So you have this fluctuation time, which is much smaller than exponential of plus u of x divided by epsilon, which is the typical time to see one excursion. And then you have infinite time. So here on this time scale, you see just one excursion. It would be extremely rare to see two excursions. You will have exponential of twice this factor. Okay. And so then you will see as much as you want, but you will have to wait a very long time. So then if you are working in this time range, then you can consider that one excursion is enough. The case with two excursions can be neglected. And then, because at the end, anyway, you take the limit when epsilon goes to 0, this time scale also goes to plus infinity. And so that's why the formula I have written here is correct. So all this, the derivation and so on, is explained on the lecture note with all the detail. Yes?
Does tau f come out of this theory as well?
Well, it does not come from the theory, but it is written in the dynamics, right? If you know the dynamics, you can analyze it and look at tau f. So all the time scale are included in the expression for L and H, right? Okay, so I will stop here with this formal discussion, and then we go towards application. So the suggested reading for the today's lecture. So I have lecture note for a basic introduction to large deviation theory. So there is two files, 1A and 1B, that you can find on the document that is on the website. So the first is for the sum of independent random variables, and the second for dynamical systems with weak noise. So you can look at these two files. And then you have, if you want to look at more general large deviation principle, you can look at the section 3 of the paper, of this paper. Okay, so this is, you also have a link on the file I gave. So when I give lecture with much more time at students in master and at ENS de Lyon, and typically we need 3 hours for this one, 3 hours for this one, and 3 hours for this one. It's the typical, if you want to work out all the details. Okay. So I go now to the second lecture. Where we will apply this to physical problems related to turbulence, atmosphere, and climate dynamics. But before, we will also apply it to kinetic theories. So this is the title of my second lecture. And so the first part would be to compute the large deviation that are associated to the Boltzmann equation for dilute gases. So I am very thankful to Hussein that already introduced the Boltzmann equation yesterday. So we will speak again of the Boltzmann equation and look at the large deviation associated to it. And then we will look at kinetic theory for two-dimensional turbulent flow and rare transition for the Jupiter problem that I introduced at yesterday at the beginning of the lecture. So you know the Boltzmann equation, right? Maybe you have studied it, and Hussein introduced it yesterday. So here you have a distribution function f. So it depends on position and velocity, and you look at the local probability to see a given numbers of particles with position r and velocity v. And so this distribution is just transported according to the velocity. And then here you have a collision kernel. And because we are assuming dilute gases, the particles will meet being nearly completely decorrelated, and then they will collide, and then they will live far apart. And that's why here you have a two-body process, because you have a two-body collision. And so you have the effect of the collision that collide and the effect of the collision that are, so you have four velocities. So you have velocity v prime 1, velocity v prime 2. So then you exit with velocity v1 and with velocity v. Okay, so you need to look at this process. So this one, for instance, it's proportional to the probability to have v prime 1 and v prime 2. So it gives you this term, and the other, it gives you the other term. So maybe there is a sign error here. And so this is the rate of collision between these different velocities, the collision rate. Okay, so you know that it is a cornerstone of physics because it was related to all the discussion about the atomic nature of physics in the 19th century and the relation between microscopic dynamics and mesoscopic dynamics or macroscopic dynamics. And so Boltzmann wrote this equation, and then there were a huge paradox, a huge controversy with a mathematician, Loschmidt, Zermelo, Poincaré. So the mathematician pointed out that the microscopic dynamic is time reversible, and so this equation here is time irreversible, and so you have a problem. Okay, so you have a paradox. It's not, there is no problem, but there is something you need to understand. Okay, so there is a classical explanation of this paradox, which date from Boltzmann. Actually, Boltzmann didn't understood immediately the point, but later on, he was the one that understood it the first and gave the correct explanation. But you have to understand this using probabilities. And if you use probabilistic concept, then there is no paradox anymore. And then the argument of Boltzmann have been made clearer and clearer during the 20th century by Ehrenfest, many others. And we have a common understanding of this paradox. And so, for instance, there is a nice mathematical work by Lanford in 1973 that prove that the understanding we have is actually mathematically correct. So here I will give you another interpretation, which is completely compatible with the classical one, but which is actually much simpler. And to do that, I will use a large deviation theory. So this is what you find in the classical textbooks. So this is, for instance, about statistical mechanics. All these pictures are just copy-paste from the Rife textbook about statistical mechanics. And so, for instance, you describe Joule expansion. And so you put half of the particle on the left side of the box, you open this, and then the particle go around, and then progressively they go everywhere in the box. And then you look at the numbers of particles on the left part of the box, So you start from n, which is very unlikely if you consider the whole dynamics. And then you have this relaxation, and you relax towards the equilibrium value. So the equilibrium value here is obvious just by symmetry. It is n divided by 2. So in the classical textbooks, you can read about this relaxation. There are words about relaxation towards the equilibrium, for instance, using the Boltzmann equation. In the classical textbooks, you can also read about the probability to see n particle on the left side of the box. Okay, so this is actually the Einstein formula that relates the probability to the entropy. So the probability to see a rare fluctuation is proportional to exponential of plus the entropy, or the entropy divided by kBt, right? And so this is just the Einstein formula. But what you cannot read in classical textbooks, it is, so in classical textbooks, the probability for this very rare fluctuation, it's related to the entropy. Here, the quasi potential is just the entropy. But you don't find in the classical textbook what is the probability for the fluctuation that leads you to this very rare path. So for instance, if you imagine a fluctuation here, which is very rare, but which can happen because the dynamic is microscopic, you don't know how to compute its probability. And so this is my aim here, is to complete this with someone that would give you actually the probability to see paths which are very rare, but that can occur. And so we will do that for dilute gases related to the Boltzmann equation. Okay, so this is the definition of F, right? This is just the empirical distribution. I look at the local density I have n particle with velocity Vn and position Rn. So the velocity and position depends on time. And then those are delta Dirac function, meaning that I am looking at the local density at position R and velocity V and how it depends on time. And so you have this transport, and then you have the effect of the collision, okay? As I already discussed before. So what were the hypotheses of Boltzmann to get the collision kernel I wrote before? So basically, you have assumed that the collision duration is neglected compared to the average collision time, the average time between two collisions. The collision geometry is also neglected, just like point particles. The probability of free particle encounters is neglected. You neglect the fact that you can have free particles at the same point, at the same time. There is something which is called the Strossal-Ansatz, which sometimes also called propagation. It's related to what is called the hypothesis of propagation of chaos. So basically, I reformulate it here, but it's basically this, that Boltzmann explained. At any time, the effect of this collision on the distribution function f can be quantified as if locally in space, the particle with velocity v1 up to dv1 and v2 up to dv2 would be mutually statistically independent and each distributed according to a local Poisson point process in position with the density, which are the actual density given by f. So it's a bit, it's a precise way to say that the particles just collide as if they would be completely independent statistically. And the local probability for them to collide is just given by something which is proportional to the density, the local density. Okay, so this is called a chaos hypothesis, the fact that you can neglect the correlation between the particles. And then there is a last assumption, which is never made in the textbook, but which is very important for the discussion today, is that we will compute just the average effect of the collision. And so this is something like a law of large number. We are computing just the average effect of all this collision. We neglect the possible fluctuation of the numbers of collision. So you have So you have particles that collide. So the particle will come here. They will interact. Okay, so if it is a hard sphere, they just bounce, but it could be anything else. They could interact, and then finally they leave. And so here you have the time. You have the time you pass here, and then you look at the average time each particle will travel without meeting another particle, and so you have this other time scale here. So I don't know how. So this is the collision duration, and this is the collision time. Right? And so basically, you assume that you neglect this one compared to this one. And so all this assumption, if you think about them, they are extremely natural for a dilute gas, and they will be correct in what is called the Boltzmann grad limit, for which the numbers of particles in a box which is the size of the mean free path is very large. And then you get if you make this assumption, it's very easy to write the Boltzmann equation. So here you have products of F because the particles are uncorrelated rather than two-body distribution. And then it follows very easily. The main property of the Boltzmann equation is that it conserves mass, total momentum, and kinetic energy. And the entropy, defined this way, increases along the solution of the Boltzmann equation. So the Boltzmann equation is time irreversible. It always increases the entropy. And so this is the paradox. And then at the end, you get that the Boltzmann equation converges to the Maxwell-Boltzmann distribution. And that's all what I want to say at this stage. Now, I would like to redo the same, but rather than assuming that I will compute just the average effect of the collision, I will compute the effect of any possible collision. So it can happen that you have a density of particle with velocity v'1 here and v'2, but actually just by chance, the numbers of collision will not correspond to the actual density, but it might correspond to half of the actual density. Just because by chance here, there, at this time, the particles just missed each other. They just passed. Okay. So this is possible. Okay, this can happen. Of course, it is very rare, but when the numbers of particles is large, but it's still possible. So now I redo all the computation, but computing all the statistics for these possibilities. And when you do that, it's very easy to do the computation. Yes?
Can you clarify again what are the allowed?
So I make exactly the same assumption. The particle will collide as if they are statistically independent, but I don't compute just the average effect of the collision. I will compute all the possible collision numbers and all their probabilities, right? So I forget about the last hypothesis, and I will ask what are the probabilities for this. And then if I do that, you realize that it's exactly the same computation as my network of reacting particles I had before. The point is that I have to, it's just like if I have particles of type K1 that meet particles with type K2 locally. So here K1 and K2 are just velocities, and then they collide and give particles of type K3 and of type K3 at a rate lambda. And so here the rate is just what I call the collision rate. Okay, so then I can actually work out exactly as in this case, the probability to have a very rare evolution of my local F, and I get the Lagrangian. And if I do that, the Lagrangian I will get I made the same exercise as before, and I will get an Hamiltonian where I will have this exponential factor here with minus in front of the particle that leave and plus in front of the particle that arrive. And with a rate here is just the rate of a collision. Okay, so I do that. And for the action Hamiltonian I obtain for the dilute gas will be exactly this one. The probability to see F epsilon is equal to F will be given by this action here with an Hamiltonian H, where the Hamiltonian H will be a H that corresponds to the collision plus a H that corresponds to the free transport. And here you can see the formula for the H that corresponds to the collision. So it's just quadratic in F because we have two-body collision. It's proportional to the collision rate for each of these possible velocities. Then I am integrating over the value of all the possible velocities. And then here you have this exponential factor, which are natural for these interacting particles.
Probability of the ER because this is not
So here the Hamiltonian is analytical, you have an explicit expression. So it depends on P and F, right?
Yeah,
so then, so at this stage, P is any function, right? Because then when I will have to compute the supremum over P, adding some constraints, then I will have to compute the P which is adapted to the situation I am considering. For instance, it depends. For instance, if I want to look at the most probable path, which should give me the Boltzmann equation, then P is just equal to 0. Then if I want to compute the fluctuation path, then it's much harder because I will have to condition on the state that I want to reach. Then in this case, because of the time reversal symmetry, actually I am able to compute P explicitly. But if I don't have a time reversal symmetry, in general, it's difficult, and you have to write the Euler-Lagrange equation and to find a way to solve them or to do something else. You're right. Yes? So let me, yes, let me explain again the result. Yeah. So I think you will correct me if I am wrong. I think you want to understand what we have done exactly. I mean, what is the interpretation of what we have computed? Is it what is the relevant, right? Okay, so you see here we look at the distribution F. We have Fn, which is the actual distribution when you have n particles, right? And so we look at the probability that Fn is equal to F. For F is any smooth function, right? So the probability that Fn is equal to F is given by this formula with this Hamiltonian and this Lagrangian and this action, right? Then you can, once you have this formula, you can compute any relevant that you are interested in, as we did before. So at this stage, it describes everything, right? And then you can say, well, what is the events I am interested in? So for instance, you can say, well, this is my this is F. Abstractly, this would be F. Okay, F is a function and so on, it's complex, but here I just make an abstract plot. This is time. Then I ask, what is the most probable evolution for F? Then I should see the relaxation of F. And so this is what is called a fluctuation path. So a relaxation path. And this should be exactly the same as the solution of the Boltzmann equation, right? This is what you do when you want to describe the relaxation. This is not rare. This is the typical path. But then you can ask whatever you like. For instance, you can ask, well, what is the probability to arrive here at time capital T, starting from the equilibrium at time 0? And then you get what is called the fluctuation path. And then the rare event, it is the trajectory that leads you to this fluctuation, okay? Or it could be anything else. You can ask, what is the probability to start from here and to go there and through passing through this point, that point, and that point, okay? So you can define the rare event as you wish. And then you just use this action, putting all the constraints that are of interest for you. Okay, so this action, which is very important conceptually for statistical mechanics, it was first written by Christian Leonard for the CAC model. The CAC model is a model of interacting particle without notion of space in 1995, and then by Freidun Razak move for stochastic model with Boltzmann-like behavior. So what I explain you today is something that I explained in this paper that I gave you the reference, for which, I mean, in those papers, actually, it's very abstract, very mathematical, and you don't really understand the basic and the heuristic things. And so what I did in this paper is to explain it in very simple terms for physicists and to relate this to the irreversibility paradox and to explain how it is related to the irreversibility paradox. And then recently, there are some mathematical results that prove that for the actual collision with Hart sphere, then for very short time, mathematicians are able to prove that this is actually correct. But the hypotheses we do, which are the same as Boltzmann, are actually correct. Okay. And now if you look at the quasi potential for this problem, well, you find that it is minus the entropy, as expected. And so it's completely compatible with equilibrium statistical mechanics. It's completely compatible with Einstein formula. And here it gives you the probability for any path. What is the relation of this with the irreversibility paradox now? I should speak of reversibility for a stochastic process. Okay, here we have Hamiltonian dynamics that describe these particles, or the quantum mechanics that describe these particles, and those are time reversible. Then I describe the dynamics mesoscopically. So at a mesoscopic level, once I have taken this limit of a dilute gas, I have a stochastic process. And so I want to know if this stochastic process is time reversible or not. And so when you speak with a stochastic process, you have a simple definition of time reversibility, which is called detailed balance. So if you look at detailed balance is written here. So you look at the probability to be at X, the stationary probability with S here. You look at the transition probability, the probability to go from X at time 0 to Y at time T. And then if you have this equality here, where you see that there is a symmetry between transition forward and transition backward, then you call this detailed balance. And so this is called detailed balance condition. Then for n particle, if the n particle dynamic is time reversible, for instance Hamiltonian, then we expect the stochastic process of the empirical distribution to be also time reversible. Then we should be able to write the consequence of this detailed balance on our large deviation principle. And so if you do that, again, it's a simple exercise that I do not reproduce here. You see that detail balance at the level of large deviation appears as a symmetry for the Lagrangian or for the Hamiltonian. And so the point here is that this symmetry, you can check it for the Hamiltonian I described before. So it means that the path large deviation I have written for the Boltzmann equation is time reversible, as interpreted as the time reversibility for a stochastic process. And so the large deviation action does not break the time reversibility. Then there is no more irreversibility paradox, because we expect the large deviation action to be time reversible symmetric, and it is. So the point is that the time reversal symmetry is not broken neither by the mesoscopic description nor by the Strossal ansatz. And so it's very different. When you look at a textbooks, it's often explained that you break the time reversal symmetry because of a Strossal ansatz. So this is wrong. You can still keep the Strossal ansatz without breaking the time reversal symmetry. The only point is that you should then look at all the probabilities and not just the average. And so if you do that, you get a large deviation principle, which is time reversible. The point when you break the time reversal symmetry, it's only when yourself, you ask, I don't care about this stochastic process, I am interested only in the most probable evolution. When it's you that, because you want to forget about the detail, you break the time reversal symmetry. And the details, you can forget about them because they are extremely rare. But if you are interested in very rare things, you should not forget about it. And so if you are interested about time reversibility, the probability to see backward path or things that are unusual are rare, so you should care about them. So you should really look at the stochastic process at the large deviation level. Then actually, because of this time reversal symmetry, you see that the fluctuation path are time reversed of the relaxation path. And you actually have the same thing as Onsager relation, but fully nonlinear. It can be as nonlinear as you wish. You can consider shocks, whatever you like. You still have the time reversal symmetry. And so you can extend the Onsager reasoning extremely far from equilibrium. And so if you think about it, with this large deviation picture, everything is very clear and simple, and there is no more any paradox. Any path is possible, and the probability for any path is quantified, and there is this time reversal symmetry, which is built in what you are computing. So what we did, and I won't talk about it today because it's technical and it's more difficult, is to extend this computation of large deviation rate function to all the classical kinetic theories. So you know this, there is a Boltzmann kinetic theory for dilute gases, but there is also the kinetic theory for plasma. For instance, you get the Landau equation for plasma beyond the bite length. And so the Landau equation, you also get it from microscopic dynamics as a law of large number. And so here we worked out the large deviation Hamiltonian for it with Wassim Feliaci. Wassim was a master student working with me. And so we also did it for systems of particles with long-range interaction, which are very relevant, for instance, for even for, I guess, active matters in many cases. And so recently with Jules Guyot, a postdoc, and Gregory Ying, we also worked out the Hamiltonian for the kinetic theory for wave turbulence with weak interaction, weak turbulence theory, when the waves interact weakly. And so for this, there is a classical kinetic theory that has been derived by Peirce in the 30s, and Sakharov and many others work with this. And so here too, it's a law of large number. You go from reversible dynamics to irreversible dynamics. But here too, we can compute a large deviation Hamiltonian and check the reversibility properties. And so I have slides for lecture about that if you might be interested, but it goes beyond what I want to talk about today. Yes. Yeah. So here what Boltzmann called chaos is not the chaos of dynamical system, right? It's just the fact that the particles interact as if they would arrive completely randomly without correlation. So this is the, and so this chaos, it's an approximation, if you like, because particles actually carry some correlation. But if you have a dilute gas, those correlations are extremely weak because particles collide and then they go very far apart. This one goes there and this one goes there. So the probability that they will come back and see them each other again is extremely small. So this is chaos in this sense. The fact that you can treat the particles as if they would be statistically independent. So here we make this hypothesis because it seems so natural when you think about what is a dilute gas, just like Boltzmann, and we get the Hamiltonian. And that's fine. For me, it's good enough. If you are a mathematician, you really want to prove that this is not an hypothesis, but in the limit, you can prove that it's actually like that all these correlations are so small that you can neglect them and so on. But when you have to describe everything, it's become very tricky. And this is what the mathematicians are currently doing and proving that it actually works this way. Yeah, this is a very, yeah, the question is, I didn't really explain why there is a relation between the large deviation principle and the fact that the entropy should increase. I have not explained you this today. So I think the question is, why is there this relation between the large deviation principle and the increase of the entropy? So it's true, I have not explained you this. So if you go in this paper for the Boltzmann equation, I explain then that for any path large deviation, you just have to use the fact that H is convex with respect to the second variable, and you can prove that the quasi potential decrease along the relaxation path. And this is very, very general. So as soon as you have a path, as you have a large deviation principle for path measure like that, you know immediately that the quasi potential will decrease. And so in this case, for dilute gases, the quasi potential is minus the entropy. And so it will increase, the entropy will increase. So you don't even have to do some computation, some tricky computation to show that entropy will increase. It is already built in the large deviation principle.
I was curious, so everything you've done here is classical. So what happened, does the same thing happen when you start treating quantum gases, quantum dilute gases like fermionic gas?
I guess so, but as far as I know, there is nobody has done that yet. But it should be the case, yes. Right. And I am not myself. I several times thought about this, tried to discuss about some specialists, but I would have to learn many things before being able just to formulate the problem correctly. So, but someone will do it sometime soon, I guess. Yes? right? No, no, you are right. In active matter, the time symmetry is broken from the beginning. So here, in order to get here, it's about the collision rate, the collision kernel. If you have Hamiltonian dynamics, then you will have symmetries of the collision kernel here. And so in active matter, you don't have this symmetry. So here, if you have symmetries of the collision kernel, because the microscopic description is symmetric, then this symmetry should carry out up to the large deviation level, and you should find again this symmetry at the level of the large deviation. But if you break the symmetry from the start, so for instance, if your collisions are dissipative, or if you can gain energy through some processes, but whatever you like, then from the start, there will not be this time reversal symmetry. So you will not get it at the level of large deviation. Right? Right? Exactly. So if you if you would consider the full system describing also your bath, your thermal bath, then everything should be time reversible indeed.
Not if you go deep enough, right? You go right down to the atomic description. It's reversed. If you do all the averaging to get you up to the equations of motion for bacteria, that is irreversible.
So the point is that if you want to describe everything, of course, this fluctuation path here can be very rare. They have this exponential factor. And so it can be that the time scale associated are so huge that they don't matter. So if they are so huge that they don't matter, you are happy with your irreversible description. It's good enough for you. And so the life is actually irreversible because it occurs on time scale which is much smaller compared to the time scale you will need to see this fluctuation. Exactly. Right.